Hi. We've been studying Markov models, and we looked at that first model where there's students that were alert and bored, and then we looked at the more realistic model, the more interesting model of countries being free, partly free, or not free. And in each of those cases, what we saw is that the process converged, right? That it went to a nice equilibrium. What we want to do in this lecture is study something called the Markov Convergence Theorem. Sounds scary, is a little bit scary. What it's going to tell us is that provided a few assumptions are met, and they're fairly mild assumptions, that Markov processes converge to an equilibrium. So this is a powerful result because it tells us what's going to happen to a Markov process. Now remember, this is a statistical equilibrium, right? It's going to keep churning, but the probability that you're in each state will stay fixed. And what we want to do is understand what are the conditions that must hold for that to be true. So let's go back, right, and think of our first example. Right? We had alert students and bored students, and we had some p that was the probability that you were alert. And what we could do is we could say, well, 0.8p plus 0.25, 1 minus p has to equal p. That's an equilibrium. And we found that if p was equal to 5/9, then that probability stayed the same. If 5/9 of students were alert, 4/9 were bored, then we stayed in those proportions. That's what we mean by an equilibrium. So what we want to do is we want to ask, what has to be true of our Markov process for an equilibrium to exist? There's just 4 assumptions. First one is you've got to have a finite number of states. Well, that's the definition of a Markov process, at least the ones we're considering, so that's always going to be satisfied. Second is the transition probabilities have to be fixed. So by that I mean that from period to period, the probability you move from one state to another doesn't change. Now, we'll talk in a minute about why that might not always be true, but for the moment, let's just assume that's the case. Third, and this is sort of the big one, you can eventually get from any state to any other state. So it may not be that you can get from state A to state C right away. Maybe you have to go through B. But as long as there's some way from getting from state A to state C, that's fine. That'll satisfy assumption 3. And then the last assumption, the fourth one, this is sort of a technicality, it's not a simple cycle. So if I wrote down a process where you automatically go from A to B and automatically went from B to A, then the thing would, churn, but the thing is it wouldn't really go to this nice stochastic equilibrium necessarily. It could be that you have all A's, then all B's, then all A's, then all B's, then all A's, then all B's. So if we rule out simple cycles and just assume finite states, fixed probabilities can get from any state to any other, then you get an equilibrium. So this is the Markov Convergence Theorem. Given A1 through A4, a Markov process converges to an equilibrium, and it's unique. So you're going to go where you're going to go. No matter whether you start with all bored or all alert, all free, all not free, you're going to end up at an equilibrium, and it's going to be the same one that's determined in some sense entirely by those transition probabilities. So if I write some Markov process like this, and I go ahead and solve for it, there's only one answer. There's going to be a unique answer for what that equilibrium is going to be. So let's think about what this means, because this is incredibly powerful. First thing, it sort of says, the initial state doesn't matter. It doesn't matter where I start. If I start with all free, all not free, all alert, all bored, right? Anything that's a Markov process, any Markov process, the initial state will not matter. History doesn't matter either. It doesn't matter what happens along the way. If it's a Markov process, history doesn't matter. What's going to happen is going to happen. We're going to go to that equilibrium. Now, history could depend on which students move from alert to bored, but the long-run percentages of alert and bored, the long-run percentages of free and not free states is going to be the same regardless of how history plays out. Intervening to change the state doesn't matter. So if I go in and change a state, like if I go in and say, let's just make a country, move it from free to not free, well, guess what? In the long run, that's going to have no effect. Now, I've posed all of these as puzzles. The initial state doesn't matter. History doesn't matter. Intervening to change the state doesn't matter. And they're puzzles because that doesn't seem to make any sense, because if you think about it, history matters a lot. Initial conditions matter a lot. Interventions can matter a lot. When you think about whether you're running a small organization, a big business, or a government, you think about, let's come in and intervene here because we're going to make the world better. This Markov process is very deterministic. It's sort of saying none of these things make a difference. It doesn't matter where you start out. What happens along the way doesn't matter. And if you intervene, it's not going to have any effect. Let's see what we mean by that. So suppose you can have, let's just think in the context of like a relationship. So suppose a relationship could be happy or the relationship could be tense. And suppose we're modeling hundreds of relationships, like a whole community of people, and we're just keeping track of how many relationships are happy and how many are tense. Well, let's suppose that these relationships have a Markov process. So there's fixed probabilities of moving between happy and tense. Well, we might say, well, there's a lot of tension in the community right now. So let's just, buy a whole bunch of people dinners and let's just move 50 couples from the tense state to the happy state by like giving them free dinners on the town. Well, if you do that, what's going to happen? Well, for a very short period of time, you'll make more people happy. But there's going to be that movement back towards tense. And the transition probabilities, if they stay fixed, are going to take you right back to the same equilibrium you were before. So there's going to be no effect in the long run on the system. So does this mean in general, we want to take these models seriously, but not too seriously. Does this mean that interventions have no effect, that interventions are meaningless? And does it mean that we shouldn't even redistribute stuff? If we redistribute happiness, or if we give these people meals, to make them happy, that has absolutely no effect either. Does this mean we shouldn't do these things? Well, let's be careful. There's a number of reasons why, even though the Markov model tells us that history doesn't matter, interventions don't matter, initial conditions don't matter, that it really could matter. And the first one is this: it could take a long time to get to the equilibrium. So let's go back to those happy and tense couples. It could be that if you make those couples happy, some of those tense couples, that eventually we're going to go back to the old equilibrium, but it could take 20 years. And if it takes 20 years, well, those intervening 20 years, there's a lot more happy couples. Or if we think about maybe only 60% of countries will be free, but if we artificially make too many free, we could have 30, 40, 50 years of a whole bunch of countries remaining free that wouldn't have been free otherwise. So even if in the long run we end up at the same place, it could be in the intervening years we still get some sort of benefit. But that idea that it just takes a long time to get there, maybe we can get a little boost in between, is still sort of, taking this somewhat negative view that any intervention we do can't matter. But yet we've got this darn theorem, right? We've got this theorem that says finite number of states, fixed transition probabilities, can get from any state to any other, then none of these things do matter. Well, let's look at these. Let's look at them seriously and ask, which of these things maybe doesn't hold? Well, the finite state thing, that's kind of hard to argue with because we could just sort of bin reality into different states. Remember earlier we talked about categories? Well, these states are categories, so we can think about which categories do we create to make sense of the world, and having a finite number doesn't seem like a big idea. This can eventually get from any one state to any other. Well, that one, maybe there's cases where that's not true. Maybe there's cases where you can go from one state to another. So that's one we want to look at. But the one we really want to focus on is this fixed transition probabilities. Because it could be that when we move from one state to another, when we move from tense to happy, or when we move from not free to free, or as more countries move from not free to free, that suddenly the transition probabilities in the system change, that there's some larger effect in these transition probabilities change. So the thing we want to focus on when we think about why history may matter, why interventions may matter, is because those transition probabilities may change over time as the function of the state we're in. Now, this doesn't mean that the Markov model is wrong. The Markov model is right. It's a theorem. It's always true. But if we want history to matter, if we want interventions to matter, then we've got to focus on this. We've got to focus on interventions or policies or histories that can change those transition probabilities. Let me phrase this in a slightly different way. If we think about changing the state of the process, like moving from tense to happy, it's just going to be a temporary effect. But if we think about changing the transition probabilities, then we can have a permanent effect. So when you think about what are useful interventions, they're going to be interventions that change the transition probability. When you think about moments in history that could be things like tipping points, right, which we talked about before, those are going to be moments in history that change the transition probabilities. So if we have a tipping point, if we move from one likely history to another, what must be going on is those transition probabilities have to be changing. So what have we learned? We've learned something really powerful, that if we have a finite set of states, fixed transition probabilities, and we can get from any state to any other, then history doesn't matter, interventions don't matter, initial conditions don't matter. Now, that's not to say that those things don't matter in the real world. They probably do. But if they do, then one of those assumptions have to be violated. Either states aren't finite, and that's sort of a hard one to disagree with. So it must be that either we can't get from some place to every place else, or that those transition probabilities can change. Now, the most likely one is that transition probabilities can change, and interventions that really matter, interventions that tip, histories that matter, are events that change those transition probabilities. So what we see is not that everything's a Markov process, but what we see is that this Markov model helps us understand why are some results inevitable, it's because they satisfy those assumptions, and why are some results not. Okay, thank you.